Today's topic is predicting products of chemical equations. So many times you're going to be required to balance a chemical equation when all you have in front of you is the reactants and the product side is blank. And you're going to have to determine how the elements on the reactant side are going to rearrange to form products. And there are 4 basic steps that we're going to follow each time that are going to help us figure that out. The first is we want to remember that opposite charges attract. So 2 positives are not going to come together, 2 negatives are not going to come together, but a positive and a negative will be attracted to each other and can come together to form a new compound. Once you've identified a positive and negative ion that are going to combine to form the compound, remember that the positive ion is always written first and the negative ion will follow it. If the charges on the positive and negative ion don't cancel each other out, it's not neutral, then remember we're going to take our charges and we crisscross them and they become subscripts for their neighbors. And then we have 7 elements, the Brinkelhoffs or the diatomic elements, that if they're not bonded in another compound with another element, they're going to be attached to another one of themselves, so they would have a subscript of 2. If they're not one of the 7 Brinkelhoffs and they're a single element, they're not going to have a subscript at all. So I created a little tune with these 4 phrases that are on the screen right now so that each time I was going to balance an equation, I would remember the steps in order. So here we go. Opposites attract, positive comes first, criss, cross, Brinkelhoff. Now you're going to try it with me. Are you ready? Opposites attract, positive comes first, criss, cross, Brinkelhoff. So if you can remember the little tune, you're going to remember all 4 steps in order. You're going to go through that each time you need to predict products, and you're going to be successful balancing your equations. Okay, so let's try a practice problem. We can see here that we have silver nitrate reacting with sodium chloride, but on the product side there's nothing written. And we have to figure out what the products are going to be when these 2 compounds react with each other. So if we remember our song, opposites attract, first thing we need to do is figure out the charges on all the ions so we'll know which ones can come together. We look up silver on the periodic table, and in the transition element, but this particular one only has 1 charge. It's a +1. The NO3, we should recognize that as a polyatomic ion, the nitrate ion, and it has a charge of -1. Sodium, we look on the periodic table, it's an alkali metal in group 1, so it's going to have a charge of +1. And then chlorine is a halogen, so it's going to have a charge of -1. So now that we see the charges, we can figure out which one's going to come together. So we should know, since opposites attract, that the silver, being positive, is going to want to combine with the chlorine of the other compound because it's negative. So now we've identified 2 ions that are going to come together. Second part is positive comes first. So when I'm writing this, the silver is positive, the chlorine is negative, so the silver is going to come first in the compound. Remember, the next part was criss, cross. So in order to figure out if the charges on the silver and the chlorine are neutral, I need to write them in and take a look. Well, remember, the silver was a +1, same as on the other side. The chlorine is a -1, so that's neutral. +1 neutralizes -1. We don't need to crisscross. And then we're left with the nitrate ion and the sodium ion. Remember, positive comes first. So the sodium is always going to come before the nitrate. Now let's see if we have to crisscross there. Sodium is a +1. The nitrate ion was a -1. So they also neutralize each other and we don't need to crisscross. And the last part was Brinkelhoff. And that only applies if you have elements that are single, and none of the elements on the product side are single. Each one is combined with a different element, so Brinkelhoff doesn't apply. Sometimes parts of that song are not going to apply. For example, if we weren't putting elements together and we were actually taking a compound and breaking it apart, we're not going to end up with a compound in the end, so we're not going to have opposites coming together, positive first. We're not going to crisscross, but maybe we need to remember Brinkelhoffs. So we go through the song each time. Sometimes a part of the song applies, sometimes it doesn't. If it doesn't apply, we just move on to the next part of the song, so we make sure that we hit every possible combination that we might need to. All right, now that we have our products written down, then we would make our inventory and change our coefficients to balance out the equation, same as we've been doing all along. So looking at these reactants, we can see they're both single elements. They're not in a compound. So the only way for the two elements to react with each other is to come together in a synthesis reaction to make a compound. So thinking of our rules, opposites attract. Well, we already know that the aluminum and the chloride are going to come together. Positive comes first. So looking on the periodic table, we know the aluminum is a +3 based on its location. Well, the chlorine is a -1. So that tells me the aluminum has to come first in the formula. The chlorine will follow. We put in the charges, +3, -1. The second part is to crisscross. That means we're going to take the charges on the ions and crisscross them to turn them into subscripts of their neighbors without the positive or negative sign. So the +3 on the aluminum becomes a 3 subscript for the chlorine, and the -1 charge becomes a 1 subscript, which we don't need to write. Okay, now that we have the correct formula for the product, we can start making our inventory and balance the equation. So there's 1 aluminum on the reactant side and 2 chlorine. Then on the product side, there's 1 aluminum and 3 chlorine. So the smallest number that both 2 and 3 will go into would be 6. So in order to get the 2 chlorine on the reactant side to equal 6, we need to multiply by 3. So we're going to put a 3 coefficient and then adjust our inventory. On the product side, in order to get the 3 chlorine that are present to equal 6, we need to multiply by 2. So we put the coefficient of 2 in front of the chemical formula, and that changes our chlorine now to 6. But that also changed the number of aluminum. We now have 2 aluminum, so we need to adjust our inventory, then go back to the reactant side and put in a coefficient of 2 for the aluminum, adjust our inventory again, and now we have a balanced equation. Looking at the reactants in this example, we just have 1 compound. The only thing this compound can do to react would be to split apart in a decomposition reaction. So we know that the hydrogen and the oxygen are going to separate. The beginning of our song, opposites attract, positive comes first, crisscross. Those 3 things don't apply because we're not putting elements together to make a compound. We've actually broken a compound apart. But the last part, for the Brinkelhoff, that is going to be important because in this case, the hydrogen is one of the Brinkelhoffs, so it has to have a subscript of 2. And the oxygen is also a Brinkelhoff, so it has to have a subscript of 2. Remember, it's very important before we start to balance the equation, we want to make sure we have the correct formulas written with the correct subscripts. Otherwise, we're not going to balance the equation correctly. All right, now let's make our inventory. There are 2 hydrogen on the reactant side and 1 oxygen. On the product side, we have 2 hydrogen and 2 oxygen. So we're going to need to double the number of oxygen on the reactant side. We do that by putting a coefficient of 2 in front of the H2O. Right away, we want to fix our inventory. We now have 2 oxygen. But there's hydrogen in that compound, so we changed the hydrogen as well, and now we have 4 on the reactant side. So now we go back to the product side. We need to double the amount of hydrogen to go from 2 to 4. So we're going to put a coefficient of 2 in front of the H2, fix our inventory, and now we see the equation is balanced. In this example, since we have a single element reacting with a compound, we should identify that as a single replacement reaction. So calcium is in group 2 of the periodic table, so when it's in a compound, it's going to have a +2 charge. The hydrogen has a +1 charge because it's in group 1, and the phosphate ion on our reference sheet tells us it's going to be a -3. So the calcium and the hydrogen cannot come together because they're both positive. So the calcium is going to want to combine with the phosphate. So we got our opposites attract. We need to remember positive comes first. So the calcium has to be written before the phosphate in the formula. And then crisscross. So we need to put in the charges. Calcium would be a +2. The phosphate is a -3. They don't cancel out to make it a neutral compound, so we're going to crisscross. The 2 is going to become the subscript for the phosphate ion, and the 3 is going to become the subscript for the calcium ion. Now, that means that the hydrogen is going to be all by itself. And we need to think of the next part of our song, Brinkelhoff. And hydrogen is one of the Brinkelhoff elements, so it has a subscript of 2. When we are creating the formulas for our products, the only subscripts that we carry across are subscripts inside the polyatomic ion, like the 4 in the PO4, for example. All the other subscripts are determined by the new compound that they're in. So the calcium now has a subscript of 3 because it has to balance out the negative phosphate charge. And the hydrogen is going to have a subscript of 2 because anytime it's by itself, that has to be its subscript. Now that our formulas are correct, we can start balancing the equation. Let's make our inventory. There's 1 calcium on the reactant side, 3 hydrogen, and because the phosphate ion, that PO4, stays together and it didn't change and it didn't splinter, we don't have phosphorus and oxygen spread out, we can keep that polyatomic ion together in our inventory to make it a little bit easier. So on the reactant side, there's just 1 of those. Now let's go to the product side. We're going to have 3 calcium, 2 hydrogen, and now we have 2 phosphate ions because now there's a subscript of 2 outside the polyatomic ion. All right, I'm going to start by putting a 3 in front of the calcium and then immediately fixing my inventory. To get the hydrogen balanced, I can see that I have 3 of one and 2 of the other. The lowest number they both go into is going to be 6. So I'm going to put a 2 in front of the H3PO4. So I can multiply that by 2. So the hydrogen becomes 6. But that also changed the phosphate ion because it's in that formula 2. And now I have 2 of those on the reactant side. Now I go back to the product side. The only thing that's not balanced at this point is the hydrogen. So we're going to add a 3 coefficient because 3 times 2 will give us 6. If we look at this equation, we should notice O2 is a reactant, which should tell us right away this is a combustion reaction. And if the other compound on the reactant side has carbon and hydrogen in it, like this one does, we should already know what the products are going to be. It should produce carbon dioxide and water. So now let's make our inventory and balance the equation. On the reactant side, there are 6 carbon, 14 hydrogen, and 2 oxygen. And on the product side, there's 1 carbon. So we take a look, there's 2 oxygen with the CO2, and there's 1 oxygen with the water on the product side, so that adds up to 3 oxygen, and there are 2 hydrogen. All right, so I'm going to start with the carbon. I'm going to put a 6 in front of the CO2 and then adjust my inventory. I didn't just change the carbon, I also changed the oxygen here. Gives me now 6 times 2 is 12 oxygen in the CO2 plus 1 oxygen in the H2O. So now I have 13 oxygen on the product side. So if I put a 7 in front of the H2O, 7 times 2 is going to give me 14 hydrogen. And again, I changed the number of oxygen. So now I have 12 oxygen with the CO2, but there are 7 oxygen with the H2O. So that's going to give me 19 oxygen. And if I take a look at the O2 on the reactant side, it has a subscript of 2. So no matter what coefficient I put in front of the O2, once I multiply it by 2, it always has to be an even number. So the reactant side can never be odd, which means I'm going to need to change that coefficient in front of the H2O because an odd coefficient gives me an odd number of oxygen on the product side, and that will never match the reactant side. So I need to keep it in a multiple of 14 because I already have 14 hydrogen on the reactant side. So I'm going to change that 7 coefficient to a 14. Now, adjust my inventory. 14 times 2 means now I have 28 hydrogen. And now I have 12 oxygen with the CO2 plus 14 oxygen in the H2O. So now the total number of oxygen I have is 26. So I need to go back to the reactant side. I'm going to double the number of hydrogen by putting a coefficient in 2 in front of the C6H14. So now I have 28 hydrogen to match the other side. There are 12 carbon on the reactant side. So now as I notice that coefficient of 6 that I initially used for the CO2 is no longer working. I'm going to change the coefficient to a 12. Now I have 12 carbon, and the number of oxygen, I have 12 times 2, which would be 24 oxygen, plus the 14 oxygen in the H2O, means that now I have 38 oxygen on the product side and only 2 on the reactant side. So what would I multiply by 2 to get 38? Well, that would be 19. And then adjust my inventory. Now all the elements on both sides are balanced. It is important to point out that not every single replacement reaction that we can write on a piece of paper will actually occur in nature. An element can only replace an element in a compound if it's more reactive than it. So we use an activity series. The most reactive elements are at the top, and the least reactive of these examples are at the bottom. So if we're looking at this example, can zinc replace the copper in copper nitrate? So we're going to find zinc on the chart, and we're going to find copper on the chart. And since zinc is higher on the chart, it's more reactive than the copper, it is going to be able to kick copper out of that compound and take its place. So in this case, we would have a single replacement reaction occur. How about this next reaction? Can aluminum replace lead to create a single replacement reaction? So aluminum is close to the top. Lead is farther down, so lead is less reactive, which means aluminum is going to be able to replace it. So the aluminum will kick out the lead and we'll have a single replacement reaction occurring. What about in this reaction? Can silver replace the hydrogen? So silver is down towards the bottom, and hydrogen is higher than it on the activity series. So that means that hydrogen is more reactive. Silver is not going to be able to kick the hydrogen out, and we would have no reaction taking place here. You did a great job today. Thank you so much for joining me. I will see you soon.